Today, I have very clearly established where we're headed next. We talked about finding derivatives. And one of the things that we do with finding derivatives is finding critical points. Now I realize that if you're following along the book, they're like, oh, dude, we're only like halfway through chapter 14. And this is very clearly chapter 15, optimization. And I go, don't worry. We'll go back and get the other stuff that we need from chapter 14. So we're going to find the critical points of this function and then classify which is a local maximum, a local minimum, or neither. And we're going to talk about all the different tools that we have at our disposal. So let's go with the first thing we'll think of, since we're sitting in a calculus class. Take the first derivative, set it equal to 0, and solve. We know that the critical points happen when the first derivative is 0 or undefined. So let's find out where those points are. F prime of x is 2x plus 2. We know we can take the derivative, set it equal to 0, and solve. So we're just solving 2x plus 2 equals 0, which tells us that x is equal to -1. We have a critical point at x equals -1. Now, if we want to classify this critical point as a local maximum, a local minimum, or neither a local maximum or a local minimum, one thing we can do is test on either side of our critical point. We can also appeal to the second derivative, which is what we want to do today. If we take the second derivative, the second derivative is a nice constant 2. So the second derivative evaluated at x equals -1 will give us 2, which is positive. So f double prime of -1 is equal to, let's see, carry the one, -1, 2. We're looking at the second derivative because we want to classify a critical point. So we look at the second derivative and how it compares to 0. In this case, the second derivative is positive. Therefore, we would say f is concave up. Therefore, f has a local minimum Now, this is just a location information. If we plug in -1 into the value of the function, we can actually see what the minimum value of the function is at -1, which might be a piece of information that we want to know about. So f of -1 squared plus 2 times -1 plus 6. So we're going to get what, is this going to be 5? 6 minus 2 plus 1, 5. Assuming my arithmetic is correct, which is not a good thing to assume. But come on, do what? Because I forgot to hit record. Oh, I'm recording. Oh, there we go. Usually the answer will be because I forgot to hit record. I'll need a reminder. It's the same reason why didn't I take roll? Because I forgot to today. Not because I consciously decided not to, it's because I just didn't remember. Now, you may have noticed I've only remembered like once or twice in 4 weeks, but that's about my average. So we could say that f has a local minimum of 5. That's the lowest value of the function. Now, since we notice that the function is has only one critical point, And also, since we know what this function looks like, we can say that this is a global minimum of 5 when it's -1. The big idea is we use the first derivative, set equal to 0, to solve, to find the critical points. Then we use the second derivative to classify the critical points as a local minimum, a local maximum, or neither of those. We did have other options. We could also have classified our critical point with the first derivative by taking -1 where the derivative is equal to 0 and seeing whether the derivative is positive or negative on either side of 1. -1, excuse me. So we could make a number line, see that the critical points split the number line where the first derivative is 0. So we'll look at values less than -1 and greater than -1, plug them into the derivative and see if we get a positive or a negative. So if I test something greater than -1, let's say 0, f prime of 0 will be 2 times 0 plus 2, which is positive. That tells us what's going on with the function. If the first derivative is positive, then the function is increasing. When the first derivative is 0, then the function is flat. Now I'm going to pick a value on the other side of -1, like -5. And check the first derivative. Here we get negative something. So we find out the first derivative is negative before x equals -1. And so we now see that the first derivative is decreasing. So since the function at -1 is changing from decreasing to increasing, that's how we can conclude we have a local minimum at -1. Now, these are not the only things that we could have done. I take this function for a very specific purpose. We know exactly what it looks like. It's just a parabola. And it's a parabola opening up. So it's going to have a global minimum at the vertex. The function x squared plus 2x plus 6 is a parabola. We'll have a global minimum at the vertex. It's a parabola opening up. Because it has a positive leading coefficient. Therefore, we'll have a global minimum at the vertex. Now, there are a lot of ways to find the vertex of a parabola, but there is only one way that we will do it as professionals. So we'll just rewrite the function in its vertex form by completing the square. X squared plus 2x, we got to figure out what will complete the square. Take half of 2 is 1 squared, it's 1x squared plus 2x plus 1 is a perfect square. So I'm going to borrow that 1 from the 6. I'm going to rewrite the plus 6 as a plus 1 and a plus 5. And the plus 1 will go into factoring of the x squared plus 2x. So if I write this as x squared plus 2x plus 1 plus 5, just rewriting by completing the square as x plus the square of the sum of x and 1, of the sum of the square of the sum of x and 1 and 5. We can just read off what the vertex is. Here we can see that the vertex is at -1, 5. This is something that we already knew because we applied calculus at the beginning. So we got a vertex at -1, 5, and that means a global minimum of 5 when x is equal to -1. Now what we need to do is take this same problem and upgrade it to a function of 2 variables. Any questions before we go on and bring this problem into this semester? Now, you can see that I just picked something else that was also easy to see. That's going to show what it is right in the equation. You see x squared plus 2x plus y squared plus y squared minus 4y plus 10. So we see right away that we're dealing with a circular paraboloid, and we can figure out where the vertex of that paraboloid is going to be, and thus the global minimum. So let's do that. This is just going to represent a circular paraboloid, and the global minimum will happen at the vertex. The most important terms here is x squared and the y squared. So we got to find out where the x and the y matter. The x squared plus 2x, we can complete the square there. We need a plus 1 to complete the square. The y squared minus 4y, half the -4 is -2, squared is 4. So I need 4 to complete the square in y. So I'm just going to write this as x squared plus 2x plus 1 That will complete the square. That'll make an x plus 1 squared. Then I'm going to gather up the y terms. There's a y squared minus 4y, and I will need a plus 4 to complete that square. Since I've used up 1 and 4, 5 out of my 10, that leaves plus 5 to be the rest of it. That's the leftover. Now I can factor x squared plus 2x plus 1. And I can factor the y squared minus 4y plus 4. So we can see that the global minimum is going to be at -1. The global minimum of the value of the function will be 5. And that occurs when x is -1 and y is 2. I've just taken the same parabola that I had from the previous problem. I moved it over. I put it into space. Oh, it was going this way before. I drew my y-axis and I just moved the vertex to where y is equal to 2. And then I rotated it about the vertical line where y is equal to 2. Any questions? It's important that walking into this problem, we have the geometry because we're going to try to make the calculus fit with the calculus that we used before. So I'm leading with the geometry because that's what we have in play. And that's why I picked the circular parabola. Kind of easy to analyze. I wanted to make that obvious. So we've got to do some first derivative set equal to 0 and solve stuff. That's going to produce x is -1 and y is equal to 2. What we want to notice is that there are 2 first derivatives now, an x derivative and a y derivative. So now we're going to come at this problem, but using derivatives. We need to take the first derivative, set it equal to 0, and solve, but we have 2 first derivatives. So let's find them both. We'll have fx at xy. So the derivative of our function, there it is, with respect to x is going to be 2x plus 2, and everything else is constant. Now I'd set this equal to 0 and solve, but there's another one. We have 2 derivatives for this function because the function has 2 variables. So instead of saying set the derivative equal to 0 and solve, we'll say set the derivatives equal to 0 and solve. And this will produce a system of equations. A pretty straightforward system of equations, pretty easy for me to solve while I'm standing up here. I always take it easy on myself if I'm going to have to do calculations standing up here. But we do the same thing. First derivatives equal 0. That'll produce a system of equations. 2x plus 2 equals 0. And 2y minus 4 equals 0. Rather than getting one equation, we end up with 2 equations. So we get a system of equations. Now this system, like we mentioned previously, is very easy to solve. But it does identify a critical point at -1, 2. Put some first derivatives, set it equal to 0, and solve. Now we already know that this is going to be a global minimum because we know a lot about this function. We're just making sure that the calculus tells us the same story that the geometry did. I shouldn't have them on the same piece of paper. They're going to talk to each other and collude. Should have turned the page. Maybe that's why they're lining up so well. The important thing to know is the process that we had before, set the first derivative equal to 0 and solve, still works for their functions of two variables. It told us the critical point, and that confirms what we had already thought about with the geometry. Now, the other question is the classify question. Right now, we're still using geometry to classify this, and we might not have that on our side in some future problems. So we're going to have to deal with the second derivative. Like in the previous problem, we took the second derivative, plugged in the point that we care about, and saw that the second derivative was positive, which made us think concave up, which made us think local minimum. The difference now is that we don't have a second derivative. We've got two first derivatives, and each of those first derivatives will have two derivatives. So we have 4 second derivatives. So it's not just going to be as easy as taking the second derivative, plugging in the point, the critical point, and seeing if it's positive or negative. We have 4 second derivatives. So we had our function was x squared plus 2x plus y squared minus 4y plus 10. And we had our 2 first partials. Fx at xy was 2x plus 2, and Fy at xy was 2y minus 4. And each of these partial derivatives has 2 partial derivatives. I have the partial with respect to x, then with respect to x again. And I'm just going to write fxx. I can't use double prime because I have x's and y's. So I'm just going to write it fxx. The derivative of fx with respect to x is 2. I also have the derivative with respect to x first, then with respect to y. We'll call that fxy. Our function is 2x plus 2. The derivative with respect to y is going to be 0. Similarly, I can have two partial derivatives of fy. The derivative of fy with respect to y, or fyy, is 2. And fyx is equal to 0. How can we interpret what's going on here with regards to this being a global minimum? If we think about the result we had before, the second derivative at -1 was equal to 2, which indicated that the function is concave up. We do get sort of that information here. Well, it's like literally the same because it's 2. But fxx, the second derivative, both of them in the x direction, is 2, which indicates that in the x direction, we should see something concave up. Moreover, when we look at fyy, in the y direction, we also see something concave up. So we see concave up in the x direction, concave up in the y direction. So that suggests these second derivatives are telling us that we have a global minimum or a local minimum. So we could read this fxx and think this function is concave up in the x direction. And we might look at fyy and think that's telling us that we are concave up in the y direction as well. Concave up in both the x direction and the y direction, that was backwards, in the y direction and the x direction will suggest that we have a global minimum. These two together suggest a global minimum. Actually, they're suggesting a local minimum. We're introducing facts that are not in evidence. Global minimum. Those two things together, concave up in the x direction and concave up in the y direction, indicate that we're looking at a local minimum. And we know from the geometry that this is the global minimum. It wasn't about doing a calculation. It was about seeing how the calculation ties to what we already know is going on in the function. Any questions? Is everybody okay? Change things up just a little bit. Uh-oh. let's suppose that we're going to have the x squared, but instead of plus y squared, making circles, we're going to have x squared minus y squared, making hyperbola. I'm making that minus, we're going to have a hyperbola instead of a parabola. Hyperboloid instead of a paraboloid. What I've already written it. I'll have mistakes. We can think about what we're going to find here. If we think about a hyperboloid, we know that a hyperboloid is going to be shaped like a saddle. We're going to have in one direction concave up, but in the other direction, come through that point, will be concave down. So hyperbolas are like Pringles, where it's bent up in one direction, but bent down in the other direction. Has everybody had Pringles before? This is a lunchtime class, so all these examples are going to be about food. And how I missed my opportunity to go out and get some Pringles and have it be like part of the classroom expenses. So I'm going to write off these Pringles. It's for work. But I ate all the Pringles, so we'll just have to work with the memory of the Pringles. The important thing is, at this point in the middle, at -1, 2, we're going to see down in one direction and up in the other direction, creating a saddle or a Pringle. I think calling them a saddle is too highfalutin for me because, you know, horses are expensive. Pringles are cheap. So we expect, just based on the geometry, to see a saddle point at -1, 2. Let's see if our calculations agree with that. Let's take a look at a picture, the saddle point. It's a high point going in one direction, but it's a low point going in the other direction. That means it's neither a local maximum or a minimum. It's going to be this saddle point. We'll call it saddle point. Let's take derivatives. The derivative fx at xy will be 2 times x plus 1 to the first. We set that equal to 0 and solve, and we get x equals -1. Fy at xy is going to be 2 times y minus 2. Set that equal to 0 and solve, and we'll get the same point, y equals 2. We have a critical point. -1, 2. Now I want to classify it by looking at the second derivative. If we look at fxx, the derivative of fxx is going to be 2. The derivative of xy is going to be 0, just like before. So that's kind of suggesting that the function is concave up in the x direction. But that's not enough. We have more than one direction going on. But when we look at the second derivatives, fyx is equal to 0, and the one we care about, fyy, is equal to -2, because I dropped the negative. Right. So that derivative fyy suggests that the surface is concave down in the y direction. That's suggesting that the function is, the surface is concave down in the y direction. Concave up in one direction, concave down in the other will suggest a saddle point. That's going to suggest that F has a saddle point at -1, 2. Or since it's a lunchtime class, a Pringles point. Yeah, that'd be a way to get sponsorship from Pringles. On my shirt, I think it's like a Pringles hat right here. And then like Texas Instruments point. Texas Instruments. And Pringles. Now let's take some notes. Let's open up our rocket book. If I do that product placement. And I'll write in it with my Pilot friction pen. Or I have to do it on camera. My Pilot friction pen. Companies don't return my calls. And then the restraining orders show up. And I'm like, oh, can I at least just buy Pringles if no one from Pringles knows that I'm doing it? And they're like, we'd really prefer that you don't. So all we're doing is taking stuff that we have an intuition for already. And we want to look at the geometry, look at the calculations, and see when our intuition is good. Because a lot of times we're told to go with our instinct, go with your gut. But if you don't have any education behind it, your instincts are going to be trash. Like if you put me out on a basketball court and say, go with your instincts, I don't have any basketball education whatsoever. How can I possibly have basketball instinct? You know what I mean? What if you do that and the only sport that I've ever played is rugby? And then like put me on a basketball court and say, use your instinct. I go, all right, my instincts are to like knock everybody over and beat them up because I'm a rugby player or something like that. You know what I mean? What, it could be worse. What if I'm like a hockey player and I go out there and the guys are like passing the basketball and I come out there with a stick and just start beating people up? You know what I mean? And furthermore, when it comes to things like probability, your instincts are always going to be utter trash. This is why gambling works. Because you don't have instincts for things like probability. There's no natural inclination. You don't understand how probability works. Our minds run games on us all the time. We like to think that we're rational creatures. We are 100% not rational. That is not our natural state. Our natural state is to be afraid and try to protect ourselves. Rationality doesn't enter into it. We are irrational creatures. The class comes from the fact that we think we're rational creatures. But we're not being rational, we're usually just rational. What are we talking about? Oh, yes. But it's nice in calculus, sometimes calculus is like, well, hey, that intuition that we built, spent all that time in Calc 1 building, look, it's paying off. Now, we're going to have to come up with a better way of using the second derivatives to classify our critical points, because we kind of got away with something here. Our mixed partial derivatives, mixed partial second derivatives were both 0. So they're going, oh, it's just kind of conveniently ignore that happened and just focus on the 2 that feeds into what we believe. That's called confirmation bias, and I can't stand for that anyway. So we're going to have to come up with a better system than this, but at least when we look at a very simple problem, just parabolas, paraboloids, and hyperboloids, we can see the elements of things that we already know, which is pretty cool, if you ask me. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day. Thanks for playing.